Hello, this is Module 3, Lecture 2, Part 1. There's no zero involved. We're going to talk about statistical process controls used in performance improvement. And in this module, we're going to talk a little bit about failure modes and effect analysis. Ultimately, we're going to talk a little bit about root cause analysis, although I'm not going to go into great detail about that. And that'll be in a later part of the lecture. So risk managers use lots of different methods to identify and reduce error, ranging from heuristics, such as identifying an error and tracing it back to whatever reason caused it in any way that seems to work for you. And then there's the very prescriptive methods, such as failure mode and effect analysis, root cause analysis, and many others. All of us have identified some kind of error. We traced it back to the cause of the error, fixed it, and in some cases, made it go away, or at least limited the possibility of it. For instance, come in the house at night, flip the light switch on, nothing happens. What do you do? Well, you can either call an electrician, which is kind of dumb, or you can figure out what's going on. Most of us flip the switch a couple of times just to make sure we actually flipped it. Then we'll grab a flashlight or hit another light switch to light up the room. Grab a ladder if necessary, check the bulb. If the bulb's working, then get downstairs and check the fuse box or the breaker panel, whichever you have. And if there's a problem there, then you reset the fuse, you replace the fuse, reset the circuit breaker. Frequently, what you're going to find is a bad bulb. The next thing you do is think about, well, in my case, I noticed that the last few bulbs I've replaced have been incandescent bulbs, which means they're burning out faster. We all kind of knew that. So I've replaced a lot of those with those little circular compact fluorescents, and I'm replacing bulbs probably once a year instead of once a month. That works pretty well. But it's a really simple problem, and it's one that you've run into every day. It's kind of a daily life example of a very common problem. More prescriptive methods can be used for determining causes that are a bit more complex. They'd be kind of superfluous in this instance. The examples that really touch our professional lives are the ones that tend to be challenging, complex, associated with much higher stakes, patient pain, or high cost, association with some kind of a never event. For these, we need robust, reliable, valid, repeatable, defensible, and documentable methods. For decades, manufacturing has been using these types of methods. They've built on these criteria, met these criteria, and healthcare seems to be following very, very far in the wake, with very few exceptions. Mostly healthcare relies on these heuristic methods. Flip the switch, if it doesn't work, change the bulb. Since the IOM reports, this has changed a great deal. Lean manufacturing techniques, Kaizen, Six Sigma, other successful efficiency methods have been making their way into healthcare since 1999-2000. With these methods come equally efficient methods of finding, correcting, and eliminating error, all in the pursuit of the goal of improvement. Now, improvement can occur in all three quality areas. Structure. We can improve that by improving education, capital activities such as rehabbing an old building to improve the workspace and the workflow, and improving hiring techniques. Process can be improved by limiting the amount of time an activity takes, identifying and limiting opportunities for failure or error, correcting gaps between what ought to happen and what actually takes place. And outcomes can be improved by determining the desired outcome, observing the actual outcome, and bridging the gap between the two using reasonable and effective methods. Saying it this way, it seems pretty easy. It's not. One of the most challenging things to do is overcome that culture of blame that pervades healthcare. We've discussed this, I'm not going into it again here. From there, the next step is to determine how things are, how they could be, and where the deviations are that prevent that how it could be from happening. And these are your errors and your failures. The first topic is failure modes and effect analysis. I can't hope to teach you this very robust method in one module. But using a combination of this lecture, the readings I've given you, some more readings that I'm going to post that you're not required to read, but are just kind of nice to have, you should be able to piece together a good understanding of the basics of FMEA. The Department of Defense, which calls FMEA FMECA, Failure Modes, Effects, and Criticality Analysis, states that FMECA is an essential function in design, from concept through development. To be effective, FMECA must be iterative to correspond with the nature of the design process itself. The extent of effort and sophistication of approach used in the FMECA will be dependent upon the nature and requirements of the individual program. This makes it necessary to tailor the requirements for an FMECA to each individual program. Tailoring requires that, regardless of the degree of sophistication, the FMECA must contribute meaningfully to program decision. A properly informed FMECA is invaluable to those who are responsible for making program decisions regarding the feasibility and adequacy of the design approach. The Institute for Healthcare Improvement, and I'm giving you a link to this, defines FMEA as a systematic and proactive, and this isn't a quote, it's a paraphrase, systematic and proactive procedure that is effective for identifying which parts of the process are ineffective, most likely to fail, or need change. FMEA reviews the steps in the process, what could go wrong in those steps, why failures could occur, and the potential consequences of failures in the process. The IHI adds, and I quote, "Teams use FMEA to evaluate processes for possible failures and to prevent them by correcting the processes proactively rather than reacting to adverse events after failures have occurred. This emphasis on prevention may reduce risk of harm to both patients and staff. FMEA is particularly useful in evaluating a new process prior to implementation and in assessing the impact of a proposed change to an existing process." To start, you need to recognize some definitions important to our discussion. Effect analysis is the study of the consequences of failures. Failure is the loss of function in a device intended for use in a given situation. A failure mode is the manner in which the failure occurs or is observed. Errors or defects in a process, design, or item, especially those that affect the customer, can be potential or actual. And failure effect is the operational consequences of the failure. The local effect is the effect of the failure on immediate structure, process, or outcome under analysis. Next higher level effect is the effect of the failure on structures, processes, or outcomes immediately dependent on the failed subject. So, local effect, this broke. Next higher level effect, and because this broke, this can't occur, okay? And then there is the end effect, the effect of the failure on the ultimate outcome. This broke, this can't occur, our patient can't get better. Failure cause, the defect of design, instrument, part, or process that underlies or leads to failure. For instance, having two different shades of green on the caps of two different drugs that are in similarly shaped vials, but one is innocuous and the other one could be lethal. And severity, the worst case scenario degree of negative effect or potential for negative effect attributable to the failure as measured in system damage, property damage, injury, or lethality. I'll get back to this in the next segment.